So, welcome to the lecture series on nonlinear programming. In the last class, we have seen what convex sets are and what are their properties, and also we have seen what convex functions are, and we have also seen some examples on convex functions. In this lecture, we will see some properties of convex functions. So, let us discuss. So, what convex functions are? Function f is set, function f from a convex set to R is said to be convex if f of lambda x1 plus 1 minus lambda x2 is less than or equals to lambda fx1 plus 1 minus lambda fx2, and this should hold for all x1 x2 in S and for all lambda between 0 and 1. So, this is how we can define convex function. Now, let us discuss some examples how to prove mathematically that a function f is convex. Geometrically, we have already seen that what convex functions geometrically represent, but how can we show that a function f is convex mathematically? So, let us discuss few examples based on this. Suppose function is from R to R and f is suppose mod x. So, we have seen graphically that mod x is a convex function. Okay. How can we prove this? So, you take two arbitrary points x1 and x2 in R. Here S is R. If for this example S equal to R. Okay. So, what is f of lambda x1 plus 1 minus lambda x2? So, this will be equals to, by this definition, is mod of lambda f x1 plus 1 minus lambda x2, okay, lambda between 0 and 1. Now, this is less than or equals to lambda mod lambda x1 plus mod of 1 minus lambda x2, because mod of a1 plus b1 is less than or equals to mod of a1 plus mod of b1. Okay. Now, this lambda is a non-negative value, so it can be taken out from the modulus. Again, 1 minus lambda is also non-negative because lambda is between 0 and 1. So, this also can be taken out. Now, mod of x1 is nothing but fx1 and this is fx2. So, we have shown that f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda fx1 plus 1 minus lambda fx2. So, that is how we can show that mod x is a convex function. So, we see some more example based on this. Suppose very simple example, suppose fx equals to 3x plus 4 and we have to show that it is a convex function. So, again you take lambda x1 plus 1 minus lambda x2 for any x1 x2 in R and lambda between 0 and 1. So, this is equals to 3 times you apply this definition lambda x1 plus 1 minus lambda x2 plus 4 for lambda between 0 and 1, and for any x1 x2 in S, S is R here. This is further equal to 3 lambda x1 plus 3 times 1 minus lambda x2. Now, this 4 can be written as 4 lambda plus 4 into 1 minus lambda. The sum is, this sum is 4. Okay. So, now this can be written as lambda times 3x1 plus 4, you club these two terms and club these two terms. Okay. So, this is plus 1 minus lambda you can take out, this is 3x2 plus 4. Now, this is nothing but lambda of fx1, fx1 is 3x1 plus 4 and this is 1 minus lambda of fx2. So, we have shown that f of lambda x1 plus 1 minus lambda x2 is equal to lambda fx1 plus 1 minus lambda fx2, that is equality holds. So, equality holds, that means function is convex. Okay. Now, suppose you have to show that fx equal to x square, you have to show that it is a convex function. Again we can apply the same definition, f of lambda x1 plus 1 minus lambda x2, it is lambda x1 plus 1 minus lambda x2 whole square, because fx equal to x square. This is equal to lambda square x1 square plus 1 minus lambda whole square x2 square plus 2 lambda 1 minus lambda x1 x2. Okay. Now to solve it further, we know that for any x1 x2, x1 minus x2 whole square is always greater than or equal to 0 for all x1 x2. Okay. So, using this inequality we can obtain that x1 square plus x2 square is greater or equal to 2x1 x2. So, this 2x1 x2 can be written less than equals to x1 square plus x2 square. So, this is less than or equals to lambda square x1 square plus 1 minus lambda whole square x2 square plus inequality will not change because these quantities are non-negative. So, this is equal to x1 square times lambda square plus lambda minus lambda square and x2 square times 1 plus lambda square minus 2 lambda plus lambda minus lambda square. So, this cancel out and this cancels out. So, this is nothing but lambda x1 square plus 1 minus lambda x2 square, or it is equals to lambda fx1 plus 1 minus lambda fx2. So, this is how we can easily say that f of lambda x1 plus 1 minus lambda x2 is less than or equals to lambda fx1 plus 1 minus lambda fx2. So, in this way we can show that a function f is a convex function, I mean x square is a convex function. Now, suppose you have to show that f is a concave function, some function like minus x square is a concave function. So, in the same lines we can show that minus f, I mean minus x square is a concave function. Okay. Now, what are properties of convex function? The first property is, if f and g two convex functions defined over a convex set S, then the sum is also convex. Alpha times f, where alpha is a non-negative scalar, is also convex, and maximum of two convex function is also convex. So, let us try to prove the first one, f plus g. So, then to show that f plus g is a convex function, we have to show this definition. Okay. So, you take h as f plus g. So, h of lambda x1 plus 1 minus lambda x2, we have to show that this is less than equals to lambda h x1 plus 1 minus lambda h x2. Okay. So, this is equal to f plus g of lambda x1 plus 1 minus lambda x2, because h is nothing but f plus g, and it is again equal to f of lambda x1 plus 1 minus lambda x2 plus g of lambda x1 plus 1 minus lambda x2. Now, f and g both are convex, it is given to us. So, since both are convex, so by the definition these are less than or equals to lambda fx1 plus 1 minus lambda fx2 plus lambda gx1 plus 1 minus lambda gx2, and this is equal to lambda times f plus g of x1 plus 1 minus lambda times f plus g of x2, and this is nothing but lambda h of x1 plus 1 minus lambda h of x2. So, we have shown that h of lambda x1 plus 1 minus lambda x2 is less than or equals to lambda h x1 plus 1 minus lambda h x2. This means h is a convex function, and h is nothing but sum of f and g. So, sum of two convex functions is also convex. Similarly, we can show that alpha times f is also a convex function. Now, to show that maximum of two convex functions is also convex, this we will discuss while we will discuss epigraph of these convex functions in our next class. Now, if we have suppose f1, f2, f3 up to fk, suppose we have k convex function defined on a convex set x, then the linear combination of these convex function is also convex. Okay. This can be proved very easily using the same concept. Okay. Next property is a convex function need not be continuous. Suppose you have this example. From minus 1 to plus 1 it is x square, suppose minus 1 it is plus 1, it is x square, this is, and at 1 it is 2, so this is 1, and at 1 this value is 2. Okay. Okay. Clearly this function is not continuous at x equal to 1. However, the function is convex, because if you take any two arbitrary points and join the line segment even with this point, so the chord is always above the curve. So, a convex function need not be continuous. The next property is a convex function need not be differentiable. So, of course, if it is not continuous, so if it will not be differentiable. And another example is mod x. Mod x is not differentiable at x equal to 0. However, we have seen that mod x is convex function. Okay. The next very important property of convex function, let f be a convex function on a convex set S, subset of Rn, then every local minimum of f on S is global minimum. So, what does it mean and how we prove it? Let us see. So, if the function is convex and you have find a local minimum on a convex set S, then it will be global by this property. Okay. So, what do you mean by local minimum? Local minimum means that suppose x bar is a local minimum. Okay. So, what does it mean? It means that fx bar will be less than or equals to fx for some neighborhood of x bar. You take a neighborhood of x bar, so it is for all x belongs to delta neighborhood of x bar for some delta greater than 0. This is local minimum. That means you take a neighborhood of that point of x bar, no matter how small delta is, if there exists some delta neighborhood of x bar such that for all x belongs to the delta neighborhood of x bar, fx bar is less than equals to fx, this means x bar is a local minimum. And global minimum means x bar is global minimum, this means fx bar is less than equals to fx for all x in S. For all x in the convex set S, fx bar is less than equals to fx. If this holds, then we say that x bar is the point of global minimum. Okay. Now, how we will show that if function is convex, then every local minimum is global. So, suppose x bar let x bar be a point of local minimum. Local minimum of f on S. Okay. Okay. And suppose x bar is not global minimum. So, if x bar is not global minimum, this means this implies that there will exist some x cap belongs to S such that f x cap will be less than f x bar. Okay. Because x bar is not global minimum. Is not global minimum means this inequality is not holding for every S. This means there will exist some x in S which is x cap such that f x cap such that the value of function have smaller value than function of f at x bar. Okay. And x bar is also local minimum. So, therefore, x bar is local minimum also. So, this means f x bar is less than equals to f x for all x belongs to delta neighborhood of x bar, and this delta neighborhood must be in S also. So, intersection with S, okay, for some delta greater than 0. Okay. Now, anyhow we have to establish a contradiction, then only we can say that x bar is nothing but global minimum also. Okay. So, take a convex linear combination of x cap and x bar. Okay. Take a convex linear combination of these 2 points. Now, this is the convex set S, okay, which is given to us. Okay. This is some x bar in S, and this is some x cap in S, and these are x. You vary lambda, you will get different x. Okay. For lambda equal to half, you will get a midpoint. For lambda equal to 1 by 3, you will get another point in between x bar and x cap. Now, this is some delta neighborhood of x bar. Okay. There is some delta neighborhood of x bar of radius delta. Okay, of radius delta. So, there will always exist some x which is in delta neighborhood of x bar. You see, if you vary lambda, you will get different x, and all are in between x bar and x cap. So, there will be some lambda, no matter how small it may be, there will be some lambda such that x will belong to delta neighborhood of x bar also. Okay. So, of course, there will exist some lambda belongs to 0 and 1, okay, such that this this suppose this is x tilde. This x tilde will belongs to delta neighborhood of x bar intersection S, no matter how small this lambda is. Okay. So, now you take you apply the convexity of f also. So, f of x tilde, which is nothing but f of lambda x bar plus 1 minus lambda x cap is less than or equals to lambda f x bar plus 1 minus lambda f x cap, because function is convex, it is given to us, and f x cap is strictly less than f x bar. So, this is strictly less than lambda f x bar plus 1 minus lambda f x bar. oh fx cap, okay, yeah, ठीक, okay. So this is equal to fx bar. So this implies fx cap is strictly less than fx bar, okay. This implies now this x cap, okay, x tilde, yeah, this is x tilde, okay, this is x tilde. So this this f x tilde is strictly less than fx bar, and but from this must be less than equals to fx for every x in delta neighborhood of x bar, and this x cap, this x tilde is in delta neighborhood, and it is in delta neighborhood such that this inequality hold, which contradicts this definition of local minimum, okay, which this contradicts 2. Suppose this is 2, so this contradicts 2. So this implies x bar is global minimum of f, okay. So hence we can say that whenever we are solving any optimization problem where f is a minimizing type function and is convex, then if you find any local minimum of f, it will also be global. So this is a very peculiar property of convex functions, okay. Now next is epigraph of a convex function. What is an epigraph? Let us see. So suppose S is a convex set, then the epigraph of function f is given by this definition. So what does it mean? Let us see. So epigraph of a convex function is nothing but all x alpha such that x belongs to S, alpha belongs to R, and fx is less than or equals to alpha, okay. And definitely because x is in Rn and this is in R, so this tuple will be in Rn plus 1. So it will be a subset of Rn plus 1, because this is in Rn and this is in R. So this tuple will be in Rn plus 1. So it will be a subset of Rn plus 1. So let us understand this definition. Suppose you have this function, say y equal to fx. Now suppose you take this alpha, okay, y equal to alpha, and this is some x1 and this is some x2. So you are interested to find out all those x alpha such that fx is less than equal to alpha, okay. So suppose you take a point here. So this fx is less than equal to alpha, this fx is less than equal to alpha, because this is this height and this is this height, okay. You take a point here, this fx is less than equal to alpha. Now x comma alpha are all those points which are on this line fx, I mean x comma alpha, so the fx is less than equal to alpha. You see, if you take this x, for this x, fx is only this height, okay. For this x, fx is only this height, and this fx is less than equal to alpha. If you take a point here, for this x, fx is only this height, and alpha is this, so fx is less than equal to alpha. So you take, if you take up all the points here on this line segment here to here, all other points such that fx is less than equal to alpha. Now you vary alpha. If you vary alpha, so you will get the line segment joining these 2 points such that x comma all x alpha such that fx is less than equal to alpha. So basically this is the entire region which represent epigraph of f. You vary alpha. If you vary alpha, then you will get all these point in the shaded region which denotes the epigraph of the function f. Now, you can easily observe that this function is convex, we can easily see, okay, and the epigraph of this function is a convex set. This we can easily visualize. You see that if you take any two arbitrary point here and join the line segment joining these 2 points is inside this region. So, we can easily say that if a function is convex, then the epigraph of the that function is a convex set. We will discuss it later on, we will prove it later on that if a function is convex, then the epigraph of the convex function is always a convex set. Okay. So, these are the representation of epigraph. Now, next is hypograph. So, let S be a subset convex set subset of Rn, then the hypograph of the function f will be given by all x alpha, x belongs to S, alpha belongs to R, such that f x is greater than equal to alpha. Here f x will be greater than equal to alpha, that means which region? So, for hypograph it is all x alpha such that x belongs to S, alpha belongs to R, and f x is greater than equals to alpha. So, this will be a subset of Rn plus 1. So, you can easily see, suppose you have this curve like this. So, you take alpha here and all those x comma alpha such that f x is greater than equal to alpha. So, for this we are having here, because if you take a point here, okay, for this x, f x will be this, f x will be up to from here to here, and alpha is from here to here. So, that means f x is greater than equal to alpha. Okay. So, in this way you will get this line, this chord joining these 2 points for this particular alpha. Similarly, if you vary alpha, so you will get all these chords joining these 2 points. Okay. So, the hypograph of this region will be nothing but this thing, and this function is concave. So, we can easily see that if we have a concave function, then the hypograph of the concave function is a convex set. Okay. So, the proof we will discuss in the next class. So, thank you very much.